Hello everyone and welcome to my presentation. I'm Meng Tian, a PhD student from the University of Aizu. Today I'm very excited to share our research titled A Particle Swarm Optimization with Diversity Feedback for Joint Mixed Variable Short Planning in Gamma Knife Radiosurgery. In this talk, we formulate gamma knife short planning as a mixed variable optimization problem and solve it using a diversity-aware PSO framework that jointly optimize shot locations and size. First, let's briefly introduce the shot planning problem. Physically, gamma rays from different kilometers cross each other and create a shot. Our task is to place multiple shots into the lesion area. To optimize this, our decision variables define the 3D locations, the shot size Rn, and whether a shot is activated Bn. But here we use 0 millimeters instead. This removes Bn and makes the problem simpler. As for the dose model, each shot products a dose that decreases with distance. The total dose is obtained by adding all shot doses together. Therefore, our final objective is twofold: increase the dose inside the lesion and decrease the dose outside the lesion. To solve this problem, there are 3 types of methods, but they all have limitations. Especially for swarm intelligence methods, they usually fix the shot size in advance. This limited the search, so our goal is to find a way to optimize shot locations and size at the same time. To achieve this, we use particle swarm optimization as our base, and we focus on improving its search ability in this complex space. Now let us look at our mixed variable optimization framework. The general loop is shown in the flowchart on the right. For the continuous part, like shot locations, we just use standard PSO equation here. But for the discrete part, like shot size, we use our new discrete velocity update strategy, as shown in the equation. The new velocity is randomly chosen from its own velocity, the distance to P best, or the distance to the G best. Finally, we test the update method. The results show that all shot size states are represented in the initial population, and more than 30 out of 40 discrete dimensions visit all possible states during G-best updates. This means that our method works well in discrete space. Our main idea is diversity feedback, so we must know the diversity level first. To do this, we use information entropy here, but why do we use entropy? Why not comment methods like distance or counting? Compared with traditional distance-based method, entropy is more stable. Distance-based measures can be strongly affected by a few outlier particles. In addition, some count-based methods depend on the absolute coordinate scale. Entropy is more robust and scale independent. Therefore, entropy is suitable for measuring diversity in optimization problem. Now that we know how to calculate diversity, let's see How to use it to adjust our parameters? As we know, the standard PSO has three important parameters from the behavior analyzed here. W, effects exploration, while C1 and C2 effect exploitation. We use our entropy, E, as a feedback signal to guide these parameters. Let's look at the table. First, if the swarm faces the parameter convergence, the diversity becomes very low. To fix it, we need more exploration. So we increase W and decrease C1 and C2. This matches the right side of our full graph here. On the other hand, if we have incomplete convergence, the diversity is high. This means we need more exploitation. So we decrease W and increase C1 and C2, which match the left side of the graph. Besides adjusting parameters, sometimes the algorithm still gets stuck as particles move closer to their p-best and g-best. The velocity terms gradually become smaller. Eventually, the velocity approaches zero. To fix this, just shaking the position doesn't work, because unchanged p-best and g-best rapidly pull the particles back. Therefore, we propose the sub-swarm partition strategy. When diversity is too low, it's triggered. We divide the swarm in two groups. One group randomly shakes low diversity dimensions of p-best, while another group continues the normal search. Finally, both subswarms are attracted towards the same g-best and merge back into a unified swarm. Now let's come to the experimental setting. We use a real-world medical datasite called Brain Tumors 2021. As you can see from the 3D pictures on the right, we choose 6 tumor cases with totally different shapes and size, range from 18,000 to 264,000 voxels. We compare our framework with two state-of-the-art mixed variable optimization methods. To ensure fairness, all core parameters like the fitness, evolutions, the shot size, and the weights are kept exact at the same. We conduct 10 independent runs using fixed random seeds from 1 to 10 for all algorithms. Next, let's see how our PSO performance. In this table, we plot the best results. As you can see, in all 6 tumor cases, our proposed method gets the highest mean fitness value, outperforming the two baseline algorithm. To check if this improvement is real, we did a Friedman test. The p-value is 0.0025, which is much smaller than 0.05. This means the improvement is unlikely to happen by chance. On the right, we show the 3D shot planning results for case 12. Our method displayed at the bottom successfully covers more than 202,000 boxes. outperforming the other algorithms. This shows that our method can find much better plans with higher fitness values. Next, let's see the ablation study. We want to test our two main ideas, parameter adaptation and subswarm partition. In this page, param means parameter adaptation and group means subswarm partition. As shown in the box plot, we compare 4 different settings from left to right. First, look at the second box, primer only. Compare the two, no feedback. It gives a higher median fitness. Second, look at the third box, group only. It's bringing a very significant improvement. Finally, look at the last box, primer plus group. It achieves the best and most stable performance. The box is much tighter and stay at the top, which is our optimal strategy. This proves that both of our proposed ideas are necessary. Now, let's look at some further analysis. The box plot on the left compares fixed radius and optimized radius. As you can see, when we optimize the shot size, the fitness score jumps much higher. This proves that optimizing shot size is very necessary. The graph on the right shows how the tumor dose and the normal tissue dose change with different weights from 1.4 to 1.7. As you can see, the boxes are almost flat and stay at the same level. The p-value are both larger than 0.05. This means parameter choice is not sensitive. Finally is a conclusion. To conclude, we formulate gamma knife shot planning as a mixed variable optimization problem and gently optimizing shot location and shot size. Then we propose a diversity feedback PSO framework with diversity-driven parameter adaptation and subswarm partition. Experimental results on 6 brain tumor 2021 tumor case show that the proposed method is effective. For the future work, we will incorporate clinical dose volume constraints and improve discrete optimization strategies. And finally, we want to extend the framework towards multi-objective shot planning. That's all for my presentation. Thank you very much for your time and listening.